Okay, so you can see this okay?
Mm-hmm.
All right. So like I said, the reason that we constructed this stand, it had to do with an issue that we're having with the original standard. And to explain it and why we, put the conductors, wound the conductors the way that we did, was that if you look at the IEEE standard, then there's a toroid. The idea is that you come in, you put in a voltage on one side, and then you have a test winding on the other side. So I'll call this V sub S for secondary and this for V sub P. But this is going to be connected to a voltage source. So this is V sub P. And the idea is that I energize this winding with V primary, and then I get magnetic flux goes through the winding. So this is denoted capital Phi. And then, and I'll go over the equations here in a second, but basically my test winding based on the number of turns, I can get an expression for the flux linkage. Okay. Here's the fundamental reason why this is not a good method and why we wrote the paper and patented what we did. So imagine that I now take a cross section of this magnetic core here, and let me draw this in the XY plane. So this is spherical, a core. So let's just say for simplicity, actually, no, I think that the core that's used in this paper is actually a square core, or sorry, has a square cross section. So if I take a cross section of the core here, it looks like this. So that's a cross section of the core. Mm-hmm. So the problem is when I energize this toroid, once the material becomes magnetically saturated, it's very difficult to push more flux through the core. So what happens is you actually get leakage. You get leakage flux here. So I'll call that phi sub L and this phi sub M. And not only that, but you also get, if I would draw the magnitude of the field inside this toroid, then, so let's say that let me take a cross section here. Let me take a cross section here. So that's this. Then what would happen if I drew the magnitude of the field inside the toroid? What would happen is that you wouldn't have a continuous flux, or you wouldn't have an average flux that looked okay and nice continuous across the surface. What would happen is that you'd have bunched up field lines, because you would have localized saturation, because right next to the windings themselves, you get a really strong field, but then inside the material, it's not as close to the windings. So if you imagine a set of equipotential surfaces here,
they get really dense towards the
not even, right, exactly. So because of that can pretty drastically affect, especially when you're in deep saturation, it can affect what your BH characteristic looks like. So if I would go in, I'll show this in a second, but if I can relate the field H to the flux density B, I'm looking for this anhysteretic curve that looks like this. But what happens is that because I get this localized saturation, I don't get the actual curve that I would expect. I would get something like this if I measured this. I'll get something that was okay in the linear region and then would not be accurate in deep saturation. So that's why this 1991, or sorry, 393/1991 standard didn't work for us. It does, like I said, it works in the linear region, no problem, but we were interested in getting an expression that would give us the magnetization way out here in deep saturation. Just so you know, the reason that's important is that if you go and design a magnetic component so that you're maximizing energy density, you actually have to know where this knee of saturation is. This point right here is really important. And so the problem is, it even comes up in my drawing here. Here, this is telling me that's where the maximum point is. On the lower drawing, maybe this is the knee. So that difference of, let's call it generally between 10 and 20% makes a big impact.
Sure.
So what we need is something that we could drive into saturation. Now hopefully now you can see, suppose that I could create a system where I have, here's my toroid. Let me go back to green. Here's my toroid. And now I say, well, what if I could put a conductor through here? It's actually a bundle of conductors. If I put a conductor in here, through the toroid that has a current I, then I will get a field through the material, or magnetic flux density. Those we can relate those two, but this is the field. Using the right-hand rule, the field is going to go basically around the toroid. But as you see here, I don't have any localized saturation because the toroid
directly on the
exactly. Toroid. Yeah, the toroid is far enough away from that conductor, and then what we do is we say, because ultimately I have to form a loop. So what we did was we said, okay, let's create our loop so huge
that the other parts won't impact the hysteresis curve.
Yeah. So the return conductors don't affect the field inside the conductor or inside the toroid.
But you do have a secondary winding that is. Oh, go ahead. I'm sorry. I'm jumping the gun.
No problem. Well, So the pickup winding or the test winding doesn't actually have current going through it though.
Oh, okay.
So it doesn't cause saturation at all. All you're doing is measuring the voltage across it.
Okay, that's okay. Yeah, that makes a lot of sense.
Yeah. Okay. Well, let's. And again, I know that you just took magnetics, but for the benefit of maybe other people that are watching this that need a refresher, let me just go ahead and show you how I got to the expression lambda hat, which is the theoretical flux linkage. And I think you probably already worked through this, but again, let me show this for everyone. So, couple definitions here. Magnetic flux, if you recall, using the symbol capital Phi, then this is flux density B dotted with surface vector dA over, and I'll just use a script A over some area.
Sure.
So in that case, here's my surface area, and I'm looking for, those should all be the same length, but I'm looking for total flux through the surface area. So this is phi through here, and then B is a flux density. Okay, so then we can also relate flux density B in a ferromagnetic material. That's given by B equals mu, which is the magnetic permeability. Generally, you can write it as a function of H times H. So,
and
like I said,
I'm so sorry.
No
sorry. Can you speak just real quickly to is that the defining characteristic of ferromagnetic, that you can relate the flux density to the magnetic field in a linear way?
Okay, yeah, good question. Let me switch the page and I'll show you that. So this is magnetic permeability. Okay, so why can I do that, or why can I say that? Is it always true? Yes, in general, basically with flux density. Now it's actually a vector, but let's assume that we're looking in one direction. So I'll skip the vector notation. But basically, you have flux density is composed of two parts. This is the permeability of free space. So flux density is always, this is always true. It's just a fundamental law, is that the flux density is always mu zero times h plus mu zero times this term m. So this is magnetization. But the basic idea is that flux density is always composed of the field that is basically a free space field and also a field from bound charges. So what that means is, suppose that I have, here is a block of some type of ferromagnetic material. It could be iron, for instance. And I'm going to put a field, I'll generate an external field here that goes in this direction. Now I can generate that field, for instance, by wrapping this whole thing around a coil. So for instance, if I had coil that looked like this, and I put current through it, then the way that I've drawn this, it's kind of hard to see the drawing here, but I think this would be going down in this case. But you get the idea. I would have a field that would go through that coil. Okay, that's why you see those in circuit boards. Okay, so suffice it to say though, I have a piece of magnetic material here. I put an external field through that material. Then what will happen is that if it's ferromagnetic, it will actually generate, it has, I'll explain maybe a little bit how this works, but basically this material will actually have a magnetization M, which arises from, it's actually an atomic effect inside the material. It causes a magnetization. It's from bound charge, but just imagine that inside this material, to use the classical interpretation of an atom, which isn't actually true, but I can draw an atom like this. Let's say here's a nucleus. In the classical picture that has the electrons out here circling.
Sure.
Well, if I consider this as a loop of charge, we know that it's really a cloud, but assume for a second that it's a loop of charge. Then using the right-hand rule here, I would have an H. I would have a field that would come out of this. So imagine that inside the ferromagnetic material, there's this crystalline structure that has a bunch of atoms. They have bound charge, and those bound charges are giving a magnetization vector.
Sure.
If you've taken a quantum class, you know that there's a quantum magnetic number. That's what this is coming from. So anyway, and actually a ferromagnetic material is special in the sense that if I put an external field H through the material, there's sort of this constructive addition that sort of, it's almost like an amplifier for flux. So I put magnetic flux through the material. It really likes flux, and it actually amplifies the bound charges. It aligns little magnetic dipoles in the material and gives a net increased magnetization. It's a very, very amazing property, actually. Whereas most materials, as you know, if I would take some other, like wood, for instance, it's not going to do that. It's gonna be neutral to it usually, or it'll be such that it actually neutralizes the field. So copper, for instance, will completely neutralize the field. Okay, but these special properties, these ferromagnetic materials that we're talking about will actually additively construct based on that H. And so basically then what happens is that I have my flux density, I get this, this component. It's actually, let me just draw this real quick. This flux density is a vector addition of the free, or let's just say electrons in a conductor or electrons in air, or whatever it is. It's sort of free charge, and then this one from bound charge. Okay, now here's the thing. If I go and, well, I can model it or measure it when I do that. So here's field versus B. Neglecting hysteresis effects, it looks like this. So basically it has this linear region and has this other, you know, it's generally nonlinear. So we know that I can write this as, you know, some function of H, a nonlinear function. But it turns out that you can generally write this, sort of split this out and split this function f up into two, one called mu and the other one called the field itself. Mm-hmm. So I'm just looking at it and saying, okay, well, it's a nonlinear function, and like I said, it turns out you can split these as such. But to your question, yes, you can always write this like this. So basically, B is mu 0 H plus M, which equals mu 0 H times H. So then you can even, you can say, whoops, I should have been mu. So here's my function mu of H. So therefore you can see why mu is a function of H, because this is, whoops, right? And this magnetization here is a function of H. So generally you can write mu as a function of H.
Okay.
Okay, now, so given that is true, so I've got this equation, let's go a little further. So you'll probably remember this one in magnetics, basic magnetics, that if I have a conductor with current I, then my field lines around this one, use a different color. My field lines around here H will, you know, they'll be
the concentric circles around
circles around it.
Yeah.
And then you probably derive this already, but let's go ahead and say, let me say that this right here is a point x prime y prime. Then what is H here? At some point, or I could also just, you know, in polar coordinates, I could say at this position R. So to get that, we use Ampere's law. So this will be over a total length L dl equals I enclosed. But I know just by looking at this, I know that H, if I draw this, let me draw this in polar coordinates. This dot in the center here will be current coming out of the page. Mm-hmm. So this is X, Y, and then what I want to know is here's a circle around the conductor. It's supposed to be a perfect circle. And this is a little dl vector. This is R. This is d phi. So So then we have that. So I know that H, I'll just use capital H for the magnitude of the field. I know that it must look like this. So basically I've got H is going to look like that. Mm-hmm. And actually that the DL vector looks like that too. So basically those are parallel. So I've got that. And then I have that DL, that vector is going to be whatever the magnitude of it is, phi hat. So now applying Ampere's law, I have, oh, and the other thing is DL is going to be RD phi. Mm-hmm. So that's in this case, I've got H, RD phi, 0, 2 pi. So 2
pi H.
2 pi RH equals I. And therefore magnitude of H is I over 2 pi R. Now this I though, if I have a bundle of conductors,
is Ni.
I think I called it N sub P over 2 pi R. Okay, so we have that, and then, so the field drops off as 1 over R. Then what we can do when we get the flux linkage, or to get the flux linkage, if I draw this in the XY plane, so Y, so here's a cross section of that toroid. We've got the other side over here. Mm-hmm. So I slice that donut. Okay, and I don't know what measurement that I use for this, but let me just call this R.
I think it was RI and R out,
R inner, R outer. Okay, so I'll define those two. Then this sliver of area here, let me say that this is W. This sliver of area dA is WR or WDR. So then if I want to compute what that flux is, it's going to be a function of position R. Mm-hmm. Then, okay. Then I have that phi is going to be, now remember this was B dot dA, but B is parallel to A. Mm-hmm. So this is going to be 0, R sub I to R outer, mu of H, H, W, dr. So this is just B, and this is dA. But this is going to be Ri, R0, that permeability mu, Pi, 2 pi R, Pi over 2 pi R, W dr. So I can compute this if I know the form of mu in terms of some parameters. Okay. So, and then flux linkage, and by the way, this is, let me draw a hat here because that means theoretical or estimated. So flux linkage is just the number of turns. In this case, it's going to be N secondary on the test winding. It's going to be N secondary times phi. That's just by definition. So this is just NS times all of this stuff. But so I have a theoretical expression for this. And by the way, sometimes when we write a function that's it's a function of a variable and parameters, we write the variable and then put a semicolon and then put a parameter set. So I'll just call this theta. That's a vector of parameters. But if I have an assumed form for permeability, then certainly I can do the integration, and that's what we did. And then the question is, okay, well, I've got the theoretical flux linkage. How do I get the how do I compare it to a measured flux linkage? well, if I take the cross section of the core, well, let's say then I also have a winding, and I wind it around here several times. So I'll call this V sub S. So it's open circuited by, I put a voltage source across it. Then another law that we have, this is Lenz's law. This says that that voltage is going to be d lambda dt.
Isn't it negative lambda?
Yeah, I'm not considering that here, but that's true. It just depends on, you know, how you where you're referencing from, but sure. So then in this case, lambda t then is of course 0 to t vs. Generally this vs is a function of t, but I'll use tau as a dummy variable plus lambda 0. So let me just neglect this one for a second. Just assume that vs has the opposite polarity, or you know, I take the measurement, then I negate it. So basically now I have a measured flux linkage as well from that test winding. And then we say, okay, well, how do I go back and determine the theta, the unknown parameters theta, and that's where the optimization procedure comes in, because basically I go and search through all of these parameter values of that nonlinear function so that I minimize the error between. So I want to find, I want to solve a problem, the optimization problem, which is theta star is arg min over all theta such that lambda minus lambda hat, this is L2 norm. So the reason I had to do this L2 norm, or like say RMS value, is because I'm actually using a time domain. So I'm taking a measurement over one cycle, then I'm getting the theoretical value also under one cycle. So I've got two waveforms, so two cycles. I've got a lambda and a lambda hat. And I'm searching for those parameters that will make those waveforms be right on top of each other with minimum RMS error. So basically, what I didn't draw right in here explicitly was that, let me do that actually. So my theoretical lambda hat is a function of my parameter vector theta. So I'm searching through all values of theta to minimize that error. Now let me stop there though. So is it clear how we, you know, how we derive this and what we were trying to do?
Yes.
Cool. Okay.
Let me ask you one quick question about this L2 norm.
Yes.
I don't know what that means.
It just means
is that bidirectional, like up and down and left and right? Is that how you're norming it?
No, it's what. So the reason I wrote it in general or said L2 is that there are other types of norms, but I think for the paper we used an L2 norm, which we're used to, like in the EE world, just thinking about it as RMS.
Oh, okay.
So yeah, but I could write a general norm that instead of taking say I've got a vector x. Let me just do two variables so it's easy. And a vector y. Then square x1 minus x2 squared plus 1 minus y2 squared. I mean, we're used to dealing with this. Mm-hmm. But in this case, I could also write this as x1 minus x2 squared plus y1 minus y2 squared 1/2. Well, the more general norm is that rather than having a 2, I might have a 3 here or 4 here. It just depends.
Right.
The norm that I want to take. And there's yeah, so anyway, that's a different subject, but sometimes when you apply fitting algorithms, it's helpful depending upon the nature of the data to use different types of norms. So, at any rate, that's the general background on why we did this. Oh, and then you're asking about this error term. So yeah, what this is, what I was doing was I was saying, so at some point we have to have so I put a current I, a bundle of current, total current NP times I through the toroid. Well, in order to get that enclosed current, at some point I've got to have the return conductor somewhere. I can't just have a current going one place and never coming back to ground. So then the question is, okay, given that I have to have that current coming back, we want to make it so that all the return conductors are symmetric, first of all, so I get cancellation in the fields, and then also they're far enough away so that the field from the return conductor doesn't affect the field that's inside the toroid, because I made that assumption of when you assume that the field has this form, you assume that the field has this form. If you remember from your physics textbook, that's a current I with a conductor going infinitely in the positive and minus direction. That's how you can derive this, because if there was a return conductor somewhere in this drawing, I would have a field, it would affect the field H.
Back into it, right?
Yeah, so this one is ultimately assuming that that's an infinite conductor length assumption going in the z plane, plus minus infinity. But we do have a return field. So then what we did was we said, okay, well, what's the difference in the error in the infinite conductor assumption versus the fact that we do have an actual conductor? And what we wanted to do is basically make sure that that error was not significant in the region of the conductor itself. So here's the individual fields from the return conductors, and then here's the field from the conductors going through the toroid. And what you basically, this is just showing a surface plot of where that error is significant. And we showed that in the region of the conductor, or the region of the toroid, which is drawn here, that error is basically, for all intents and purposes, 0.
Right. Okay.
Oh, and then
it falls off with R, right?
Yeah, it falls off, exactly. So falls off is R. So all I did was I just did a field calculation that showed this, that, well, this is the actual field. Now imagine that I use the infinite conductor assumption. I just wouldn't have these spikes here. So I took the difference between theoretical versus actual, plotted the error, and I got this 3D plot.
Why, can I ask a question? Why does the error build up farther away from the toroid? Why is there this retaining wall in this figure 4?
Yeah, that's because, so imagine, well, let's think about it like this. Let's kind of look at the extremes, because that's often a good time to see. So imagine that the conductors were right next to the toroid. Mm-hmm. Then the error would be big right around the conductors, right? Or right. If the conductors were right next to the toroid, I would expect that the difference between theoretical and measured to be large right within the region of the toroid. Right. Now imagine that I then start expanding out how far the conductors are. Well, the error in the infinite current, or the infinite assumption, and the actual is going to be most prominent right next to the conductors. And that wall is going to sort of expand as I go out.
Right. Okay.
And all we want to do is make sure that wall is very far away from the actual conductors. In our case, we just made sure that, yeah, it was very far away. Okay. Or it was far away enough. So now, suppose that in the stand we built it, and for whatever reason it wasn't out, those conductors weren't out far enough, and this wall is actually, say right here, well then we might have a problem, because we might have a 2% error or something, just because of that the assumption in our model. Right. So we're trying to eliminate that assumption. or I should say the consequences of that assumption.
Right.
So, okay, now then the question is, I wrote down this general form of the permeability, which is a nonlinear function. And then I said, okay, well, this is the trick, and this is where kind of like this is the optimization parameter ID for an optimization for finding that parameterized function of mu is an art and a science. So you have to basically look at various, kind of isolate the magnetization from measurements and say, okay, well, what does the form of this look like? Either that, or you have a basic fundamental, say, laws from physics, or like a general description of the magnetization in physics. It turned out that there was some research. There's something called the Frolic equation, which is a first order approximation of magnetization, and it has this form. It's this alpha h over 1 plus beta h. That is the form. You can derive that from basic physical principles and statistical mechanics. So, but what we did was we said, okay, well, now if I would, though, let's say that I just put mu in terms of these two parameters, I couldn't get a very good fit. So what we did was we said, okay, well, this is the first order approximation from physics. Let's then, the natural next step then would be to say, okay, well, let me take a sum of those rational functions of this form. So I have a summation in terms of these functions, where instead of just having an alpha beta, now I've got a set. I've got a number of parameters, and even to a power. So it kind of just gives me flexibility that says that's kind of a good guess, but let me add some parameters to get an even better fit. So then this m of h, and by the way, the sig function just gives you the upper and lower regions of this odd function. So mu is an odd function in general.
Right.
Okay. And then you say, okay, well, with that assumed form of m and the calculation that I did for lambda already based on the theory, now I can plug in here into this integral and compute that analytically based on those parameters. And I come up with this. Now I have something that I can compare my measured lambda to, which I get from the test winding. Then from there, it's really just applying a nonlinear optimization method, which a lot of different optimization methods could be used. Oh, by the way, yeah, so instead of saying, let me just verify it. Oh, actually, we used p equals 5. So we didn't use an L2 norm. We used basically the fifth root. That worked better for this application. Okay, but nonetheless, this part, like once you get here, is not as important, I think, for now, because there's a bunch of different ways you can use to do that parameter fit. We just happen to use a genetic algorithm. Worked pretty well. So then these two loops, the solid lines are the real magnetization loop or hysteresis loop, and then this dotted line is showing the anhysteretic, which basically just goes through that loop. And then this is just showing this is mu itself. So this is mu as a function of h. Turns out you can also write mu as a function of v, which we did here. But yeah, we got really good fits. So anyway, any other questions on the paper?
No, I think conceptually I understand what's going on. I don't know very much about nonlinear optimization.
No need on that. Yeah, so what we'll do is when we get to that step, so we'll collect all the data. So imagine you put the toroid in, you get the data, it saves it to a file, then the GUI itself will then call it's probably going to be a C function routine. All that stuff is, pretty, like I said, pretty well known. There's right. Source code out there to do that. All the GUI will do is point to the data file. The optimization will be set up, and then it'll probably show, like I want it to show the optimization happening and then show the final fit. It's just kind of cool to watch the optimization happening, and it's not just cool, it shows you how effective the optimization routine is to finding the parameters. I don't show a drawing here, but you can plot a little curve that just shows you how good is that fit getting a lot better, and do I need to restart the algorithm, all that stuff. But we'll get to that later down the line.
Okay, perfect. Well, then I had one more question, not about conceptual stuff, but I'm gonna start looking into the pulse magnetic board.
Yes.
There were two in the IEEE standard. There were two given pulse boards.
Yes.
There was I don't have it on me, but
yeah, the one that I want you guys to do is the highlighted one. Hopefully the highlights came through, but it's test circuit B.
Oh, yeah, I think it did. I for one reason or another, I don't think I put it together that it was highlighted by you. Okay.
Yeah.
And they give the what was I going to say? They give several suggested values for all of these inductors and capacitors and transistors and whatnot.
Yes.
You had mentioned a simulation program, and I wrote it down, and I don't know where I put it, but I think it was called Kai. Is that what you? Does that sound familiar?
Yeah. So there are two programs actually. When it comes to designing the printed circuit board, there's an open source tool which is actually very powerful, and I highly recommend learning this just as a student, because later on you'll probably could do this in industry. But it's called KiCad, Ki, so lowercase ki and then CAD.
Perfect.
And actually, let me just make sure that that's still available. And I just wanted to show you a picture there too. Yeah. So like you have the circuit layout if you want to, but then also you can do 3D rendering. You can learn this. I mean, you can create some really. I won't play this whole thing, but has very good built-in visualization of the board itself. And I don't know if you've done anything else with PCB boards before, but I would say you could download the software, and then there's really good YouTube videos training.
Right.
You can learn how to create. They give like simple example boards. You can learn how to create a simple example board in a matter of hours. Now, the nice thing about this pulse board is that it's super simple. But if you haven't done a PCB board before, there are some kind of like best practices to make sure that it's not noisy and things like that. And this is an opportunity for you to work with. I have a PhD student. His name is Avpri Othi, and he did a very sophisticated PCB board for an inverter that we just built. And he's really good in KiCad. So what I'll suggest then, the other thing is there's Garrett knows that Garrett, I think, and then also we had another student in the lab, Shavante Dukes, I don't know if you know him, but he created a very nice circuit board too, creating KiCad. So we've had students kind of like learn this from scratch. The reason I bring it up is that even though the circuit board itself is pretty simple, I would say get a hold of Avpri. I've already given him the heads up, and he can give you some pointers on making sure that this is, like good quality going in. Because what'll happen is, and this happened to me too when I was doing this. I was an undergrad researcher. I think I had to get maybe like at least 2 boards cut, because you basically send the company the design files, they build it, then you get it, and it's like, there's always going to be some error, that you didn't think about. So, but you can kind of reduce that time if you, I think, let Avpri see it first. I'll give you some pointers, and then we'll get those done. Now, the design files that KiCad creates, now it's set up so it's really easy. They're companies that make these boards practically overnight. Sometimes it only takes like 3 days or so, but you just send them the files, And it's usually like maybe, I don't know, could be $50 a board to $100 a board. But now the nice thing about this one is that, so it's got what, 6 passive components, 1 switch. This is the DC power supply. The toroid, of course, and then we'll use our data acquisition box for it already has a CT on it. And then this is just a signal generator, which we have in the laboratory. So I would imagine this printed circuit board to be, I don't know, maybe this large. But the only thing that we will have to consider is that it's going to have quite a bit of current going through it. So now our test stand, by the way, we ordered 14 gauge AWG for that, which I think the current rating is something like 20 amps RMS at 90 C. I'm just throwing that. I think that's about right. So now this is for minor loops and major loops. So we probably want to make sure that we can carry, around that 20 amps. And it turns out you can create a circuit board that can carry that amperage. It basically just lays down a conductor that's pretty thick, and it's essentially embedded in the printed circuit board. And like I said, Opry and Chris Lute have experience with that.
Okay.
But essentially, when you go into KiCad, you can specify any dimension of the copper traces.
Okay. Well, I'm gonna see about downloading it and then watching some tutorials, and then I'll reach out to those guys and
Cool.
start getting an idea about this.
One other thing, and this is also important whenever it comes to design, is we want to make sure that we're not actually creating a printed circuit board where we're hard soldering these resistors and capacitances on there. We want to have basically it's called a strip terminal, but basically there are these, you can buy these strips. They're usually black, and they have sort of like a spring loaded hole on one side, and the other side has a prong. So you buy these in strips. So basically we want to be able to solder on one of those strips or one of those pieces, so that we can switch out the resistor.
Kind of like a breadboard, like putting
exactly
to the top.
Now the reason for that is that I think that based on the magnetic material itself, that we might want to tune the parameters, meaning that if I really want to look at a nice minor loop here, I don't want that to get too thin or whatever the case is. So we'll want to tune this. And it turns out that Corey, for her, of course, she's helping on the GUI stuff too, but she's doing an independent study, and her independent study will be kind of like we talked about in terms of parameter optimization. She's gonna, using an assumed form of the toroid, she's gonna do basically she's gonna find those parameters to do a nice nice tuning. So if you make it general enough, then we'll just switch those out for various magnetic materials.
And we can, right. Okay, that makes sense.
Oh, and one other thing, just keep in mind that, we won't actually have the toroid directly connected as shown here. This we'll have to have some pretty, heavier conductors that can take a 14 gauge wire. So we'll have the 14 gauge wire going to the test stand here and then coming back. And then the CTs will be, coming from the data acquisition box that Garrett built.
Mm-hmm. Okay, I will take note of that.
Okay.
14 gauge.
Yeah, we ordered 14 gauge for the stand. So I would imagine this having, if you look at this just kind of as a reference, the switch and the components and everything are on the board, and then there's kind of like some terminals like this that can handle 14 gauge diameter or whatever that is, and then can handle like 20 amps.
Okay. And you say 20 amps. Okay. Well, I will see about downloading that and starting to learn about Kai.
Okay, great. In that case, yeah, go ahead.
Oh, Oh,
I was
I
gonna
was going to
say,
say thanks for meeting with me today.
sure.
I know it's not necessarily the most important feature of this project to understand all the math and stuff going on, but it certainly helps me think about it all together, like cohesively.
Oh, I would say on the contrary. I mean, this is, I mean, it's senior design, but I mean, I think of this as undergrad research for you
Hmm.
and the other students. So I actually do, like I said, I'm thankful that you went through and actually try to work through this because this is you know, like I said, very useful applications in industry, but also if you wind up taking a research path, you know, it's good to see, I guess, to go through an IEEE paper like this and like work through the math and see, you know, kind of the reasoning behind this. So I think it's good from both perspectives. So I'm glad that you did that. And yeah, thanks again.
No, not at all. Thank you for taking the time this morning.
Cool. Okay, I'll talk to you soon.
Yeah, have a great day. Have a good
You too.
weekend.
Bye. You too.